What is AutoML and so like to discuss with like how long does it take to build or tune and deploy a production ready machine learning models from scratch. Like we'll be discussing those things. What are we undergo when we create the AutoML pipelines, and also the major issues or challenges or data cleaning, feature engineering, algorithm selection, hyperparameter tuning, or feature vectorization, etc., and the model selection. And so AutoML is the process of automating the end-to-end process of applying machine learning to real-world problems and the time sync triangle. So in this, what data preparation and cleaning, 80% of the time we do these kind of activities, handling missing values, encoding and scaling. And feature engineering is on selection, 10% of the time we do this particular activities like creating new features, selecting the most relevant ones, and model building and tuning 10% of the time, which we be doing like algorithm selection, hyperparameter optimization, and AutoML goals like automate as much as of this triangle as possible. And the core concept of AutoML pipelines, like so break down the black box. So in this, what we are going to do, or what we are going to learn is like automated data pre-processing and feature engineering. So we shortly call it as auto FE. So in this automated data pre-processing and feature engineering, like imputation of missing values, mean, median, mode, using models, encoding categorical variables, one hot label, target encoding. These are the things, and feature scaling, normalization, and standardization. Important. And in the advanced things, what we do is like automatic feature generation, example, polynomial features, interactions, and selection using feature importance and correlations, and automated model selection and hyperparameter optimization as well. Or like here, systematically search for the best models and its parameters. Methods like grid search and random search uses a baseline. Explain why the inefficient. Like in the grid search, it takes consume huge time consuming, and processor and resource consumption is very high in the grid search, and it is we call it as exhaustive search, as it also exhausts the resources as well, and which is very cost sensitive. It will add more cost to the project. And random searches, in this we might miss some kind of important information when we do a random search. And Bayesian optimization, like the core of most modern automobile tools, which is the Bayesian optimization. And we already seen about the surrogate model, example Gaussian process and acquisition functions. So what is the evolutionary algorithms that we have already covered? Now we'll see the neural architecture search as an advanced topic, like automatically designed neural network architectures. Use cases primarily used for computer vision, NLP, natural language processing tasks where model architecture is critical. Example, finding a better CNN for a specific image dataset. Mentioned it's computationally very expensive but a key research area. Part 3, applications and use cases, where this is the core of the applications of AutoML question, or categorize them. And rapid prototyping and proof of concept, POC. Like scenario, like in this, we'll take the scenario: a startup needs to quickly validate if ML can solve their problem. Example, predict customer churn. Benefits or AutoML provides a strong baseline model in hours or days, not weeks. This helps in ensuring securing funding or getting stakeholder buy-in. And democratizing ML for non-experts or like citizen data scientists, scenario business analysts, domain experts in finance or marketing who understand the data but not the intricacies of ML. Tools, Google Cloud. So, to Google Cloud AutoML tables, Azure Automated ML's data robot. Benefits are allows domain experts to build and use ML models without deep programming ML expertise. Augmenting expert data scientists like scenario and experienced data scientist is working on a complex problem. Benefit baseline model AutoML provides a benchmark to beat. Feature discovery can reveal non-obvious feature interactions. Efficiencies frees up the scientists to focus on deeper problems, formulation, data understanding, and model interpretation rather than tedious tunings. Since the AutoML tuning, these are the benefits we get out of that. And hyperparameter tuning at scale, like scenario where the company has a specific complex model. In my example, custom XG boost or a large transformer, but tuning it is too slow. Tools, weights and biases, sweeps, retune, static cube flow. Benefits are like manages distributed HPO experiments efficiently on cloud infrastructure. Building end-to-end ML systems, MLOps, we shortly call them as MLOps, scenario the company needs to continuously retrain and deploy models. In this particular scenario, like what are the benefits we get as AutoML when using AutoML? Benefits are AutoML pipelines can be integrated into CI/CD, continuous integration, and continuous deployment workflows. When a data drift is detected, the AutoML systems can automatically retrain and suggest a new model. And in this, the popular AutoML tools and frameworks, like how we are going to use it, like cloud-based, user-friendly one. One example is Google Cloud AutoML, Vision LP, tables, etc. Azure Automated ML and integrated into Azure ML Studio. Amazon SageMaker Autopilot creates notebooks explaining its process. And open source code-centric auto sklearn, meta learning plus Bayesian optimization on top of the scikit-learn. And what is Teapot like? Uses genetic programming to explore pipelines, outputs Python code. AppsUsingAutoML is like very popular. Provides a leaderboard of models. Uh, FLAML like is Microsoft's one, which is lightweight, fast, and compute efficient. And in this critical part for critical discussion and limitations, like the when not to, that is a main thing when you use AutoML. The black box problem reduced model interpretability can be a deal breaker in regulated industrial, finance, and healthcare. Computational costs can be expensive and time consuming for very large data sets or complex NAS. And also domain knowledge ignored. A naive AutoML run might miss crucial domain specific feature engineering that a human expert would include. False sense of security, the model works, but I don't know why. So these kind of things will happen, can lead to deployment failures. So not for cutting edge research. If you are pushing the boundaries of SOTA in CV, NLP, you likely need to custom architecture. That's not off the shelf auto. So these are the in class activities that you can practice AutoML to show down. So that's the end of these applications of AutoML. Next is search techniques in AutoML. In this, we are going to learn about identify the core search problems within the AutoML pipelines that are hyperparameter optimization, HPO, and neural architecture search and hash. Uh, and core concepts and lecture outlines part on the hook and the problem definition. That's what we call it as. What is a hook? Like why search? Pose a question like when I ask these kind of questions, like what have a random forest model? It has over 10 hyperparameters, n estimators, max depth, min samples, split, etc. So when you talk about this, we need to understand uh, because each can take a numerous values in this scenario. The search space is vast because it's a random forest. How do we find the best combination? Like that is also one big challenges when we take these kind of problems. Like core problems, AutoML automates the black art of the model tuning. The fundamental challenge is that the performance functions of a method, performance function of an ML model, example validation accuracy is Like black box, we don't have a gradient. We can only query it by training and evaluating a model. Noisy, the performance can vary slightly due to random seeds, data shuffling, etc. Expensive to evaluate each query. Training a model can take seconds, minutes, or even hours. So, how do you conclude? Like we need efficient, intelligent search algorithm to navigate this complex, expensive landscapes. And another one is search space formalism, like introduction of the common formalism for all search techniques. So here is an argument: x is equal to or max underscore of x in x of f of x, where x is a configuration, a set of hyperparameters or a neural network architecture. This capital X is the search space, all possible configurations. F is the objective function, example validation accuracy, negative MSE, and X is the optimal configuration we seek. The part three is a taxonomy of search techniques in AutoML, category a uniformed search baselines, grid search mechanics exhaustively search over a predefined set of values for each hyperparameters. Analogy like searching every single seat in a movie theater. Pros embarrassingly parallel, simple to implement. Cons suffers from the curse of dimensionality. The number of evaluations grows exponentially with the number of parameters. This is one of the challenges, and highly inefficient. So we need to avoid these kind of grid search, and when to use only for very low dimensional search spaces, 1 to 2 parameters. Random search mechanics randomly samples configures from the search space. Analogy randomly checking a fixed number of seats in the theater. Pros surprisingly efficient, easily parallelizable, avoids the curse of dimensionality. Cons can miss optimal regions, no learning from past evaluations. And key insight Bergstra and Bengio 2012. For most high dimensional spaces, any given configuration is likely to be poor. Random search often finds a good enough configuration was faster than grid search. So when to use these kind of things? A strong, simple baseline for any HPO tasks, we can use this grid search. So category B, informed sequential search. In this Bayesian optimization, the workhorse of HPU and hyperparameter optimization. The core idea is like use past evaluation results to form a probabilistic model of the objective functions f, and use this model to design the most promising configuration to evaluate next. So this is what happens in this AutoML when you use the Bayesian optimization. Two key components is surrogate model and acquisition function, and common acquisition functions. Like mainly the surrogate model, the model that approximates the black box function F, typically a Gaussian process, which provides a mean and uncertainty variance prediction for any x. Acquisition function is something like a function that uses the surrogate prediction to quantify the utility of the evaluating a new point. It balances exploration, probing uncertain regions, and exploitation, probing regions predicted to be good. Common acquisition functions like expected improvement (EI) and upper confidence bound UCB. In the Bayesian optimization loop, like you see, these are the things will be there, which is build or update the surrogate model using all previous evaluated points x, comma f of x. Find the point x that maximizes the acquisition function. Evaluate the true expensive function f of x that is train the ML model. Add the new x, comma f of x back to the history. Repeat until a budget, time, or iterations is exhausted. Pros: highly sample efficient, requires far fewer evaluations than grid or random search. Cons: overhead of optimizing the acquisition function. Surrogate models like GPs don't scale well to very high dimensions greater than 20 or massive number of observations. Tools are we whatever we use like Skykit optimize, Bayesian optimization. Optuna uses a tree structured Parson estimator TPE, which is related. And next category is based on the population-based searches, which is evolutionary algorithm, genetic algorithm. Core idea like mimic natural selections. A population of candidate solutions model configuration evolves over generations. Key steps are initialization, selection, crossover, mutation, evaluation, replacement. Initialization: create a random population of configurations. Selection: select the best performing, fittest configurations as parents. Crossover mutation create new child configurations by combining mutating the parameters of the parents. Evaluation train and evaluate the new child models. Replacement form the next generation by selecting the best from the parents and children. Pros are very flexible, can handle complex search spaces like neural architectures, naturally parallelizables, and cons or can require a very large number of evaluation and computational expensive and many hyperparameters itself, mutation rate, etc. When to use these things are ideal for neural architecture searches, NAS, where the search space is non-differentiable and discrete example types of layers, connections, tools, or teapot use GP or deep. And part four in this, like mapping search techniques to AutoML components, hyperparameter optimizations for standard SPO for standard ML, sklearn or XGBoost. And default choices are optimization, Bayesian optimization, example in HyperRopt or SkyKit optimize. It provides the best trade-off between efficiency and effectiveness. Quick balance baseline is random search. That is one. Neural architecture search NAS as a search space. Discrete choice, number of layers, layer types, activation functions, connections, common techniques, reinforcement learning, early NAS papers, example No and Lee, used an RNL controller trained with RL to generate model architectures, evolutionary algorithms, a very popular and effective approach. Example, Google's Amoeba Net, and well suited for the complex and discrete spaces. Differentiable architecture search darts, a more recent efficient method that relaxes the search space to be continuous and differentiable, allowing gradient based optimization mentioned as an advanced topic. This is advanced one. And practical considerations and trade-offs like budget accuracy trade-offs. The choice of search algorithm depends on your computational budgets. The budget types are like low budget, medium or high budget, massive budget, complex space. Like in the low budget, random search be used, and medium and high budget Bayesian optimization can be used. Massive budget and complex space NAS, evolutionary algorithms and parallelizations. Random search trivially parallel. Bayesian optimization inherently sequential can be extended with the batch or parallel versions, example using QEI. Evolutionary algorithms naturally parallel evaluate entire population at once. Multi-fidelity optimization are crucial speed up techniques. Idea this use cheaper or low fidelity approximation of f of x to weed out bad configurations early. Examples for this are successive halving hyperband, train many models for a few epochs, keep only the top half, repeat with more resources. This is the core of HyperOpt, sklearn, and many more HPO libraries. In close, that's all about this. That's all about implementing search techniques. And before what we have saw is applications of what. Thank you all.